So the idea of two-sample hypothesis testing can be applied to proportions the same way that we just looked at applying it to means. So in this video, what I'm going to do is I'm going to walk through the first example and give you a little bit of that theory, but then show you the tool that we're going to be using in the calculator. And then in the second example, it's just going to be completely calculator based. So in this first example, it says, suppose that a drug is being tested for its ability to combat a particular illness. 120 patients suffering from this illness take part in a clinical trial to test the new drug. Using random allocation methods, 70 patients are administered the new drug and 50 patients are prescribed a placebo. The results of the clinical trial showed that 57 of the patients receiving the new drug showed improvement, while only 26 of the patients on the placebo showed improvement. So once again, you can see that we have two groups, and let's label our two groups. Group 1 is the new drug group, and in that group we saw that 57 out of the 70 patients who were administered the new drug improved. So this is our first sample proportion. You could call this p hat 1. So p hat 1 is 57 out of 70. And if you calculated what 57 out of 70 is, it is that 81% that you see right there. Group 2 is the placebo group. And in the placebo group, we have a sample proportion showing improvement of 52%, but that was 26 out of the 50 people who were prescribed the placebo. So 26 divided by 50 gives you the 52% that you see in the problem. Now, as you might recall from before, the p-hat distribution is approximately normal as long as certain assumptions are met. And so if we look at p-hat 1, it has a mean of p1, where this stands for the true proportion of people in the population who would improve on the new drug. And p2 hat also has a distribution, and the mean of this distribution, that is approximately normal, the mean of this is p2, which stands for the true population proportion of people who would improve on the placebo. So the tricky thing is, in our problem, when we look at p1 hat minus p2 hat, and we get a difference of sample proportions, let's take a look at what that difference is. 57 divided by 70 minus 26 divided by 50. We get a difference of proportions of 0.29. And when we get this difference of 0.29, we don't know if that's a good point estimate because we're not sure where our point estimate of 81% or 57 out of 70 is in this distribution, especially relative to this all-important figure. Just as we don't know where 26 out of 50 or 52% is in this distribution of sample proportions. So this could be an accurate reflection of the difference in the proportion of people that would improve on the new drug, but it also could be incorrect because it's just a point estimate. But once again, p1 hat minus p2 hat, the difference of sample proportions is also approximately normal itself. And the best part about this is the mean of this is p1 minus p2. And this is ultimately why we end up using this new distribution, because this mean is going to allow us to do some hypothesis testing and ultimately compare the true population mean in group 1 that would, or the true population proportion in group 1 that would be improving to the true population proportion in group 2 that would be improving. Okay, so let me scroll down and then set up our hypotheses here. So the null hypothesis in this case would be that there's no difference in the proportion that would improve in the two populations that we have here. And so P1 minus P2 would be equal to 0. So you can see that this would be set up a lot like the way that we set up the two-sample hypothesis testing for means questions involving the difference of means. The alternate hypothesis, though, is that the proportion of people improving on the new drug is going to be greater than the proportion of people improving on the placebo. And so that's kind of what our point estimate suggested, but now we're going to be able to confirm things with p-values and all of that, or potentially confirm things. Let's see what the results are. So if our assumption is that there's no difference, and remember this also means p1 is equal to p2, then this is 0 right in the middle of this distribution, and so our result of 0.29 is going to be out here somewhere. And essentially what we want to capture is the probability, assuming that this is 0, that there is no difference, the probability of observing something as extreme or more extreme than what we're actually observing. So we would want to get this area. And when we go to the calculator and this time use 2PROPZTEST, we're going to be able to enter the pertinent information and it's going to tell us what this area is in the form of a p-value. And so let's go to 2PROPZTEST, plug in the relevant information, see what our p-value is, and draw some conclusions. So I'm going to press Stat, Test. Now 2PROPZTEST is down at number 6. So I'm going to go down to number 6, and you can see that I've got a group 1 and a group 2. X is always the number of people that meet a certain characteristic, which in this case it's the number of people improving, and N is always your sample size. And so 57 is our X, 70 is our N for group 1, 26 is our X, 50 is our N for group 2. So we'll say 57 and then out of 70 for group 1, and then 26 out of 50 for group 2. And then let's make sure that we select the correct alternate hypothesis. In this case, we're hypothesizing that the proportion of people that are taking the new drug is going to be greater than the proportion of people taking the placebo. We calculate and we get a p-value of, that's not a p-value of 2.89. We have a p-value, let me write this down, 2.89, it's e minus 4 at the end of that. So that's in exponential form, and we need to actually move this decimal place 4 places to the left. And so our p-value is going to be 0.000289. And so that is a very low p-value. And at any alpha that you've seen so far, whether it be an alpha of 0.05 or 0.02 or 0.01, at any alpha that we've seen in this class, a p-value like this is going to be less than alpha. And if the p-value is less than alpha, then what do? We reject the null. So we would be rejecting the null in this case, and we would be saying, no, this, if there is no difference in the proportion of people improving on the new drug and the placebo, then the chances of us getting what we got were so unusual. So we're rejecting that null. We are going to accept that the proportion of people improving on the new drug is greater than the proportion of people improving on the placebo. And so I could scroll down and just write that in real quick. I could say the proportion improving on the new drug is greater than the proportion improving on the placebo. Okay, let's take a look at another example, and I won't go through as much theory in the next example. So let's take a look at this. It says a sample of 200 voters over the age of 60 were asked whether they thought Social Security benefits should be increased for people over the age of 65. A total of 95 of them answered yes. Okay, so 95 out of the 200 said yes, and this was in the group of people who were over the age of 65. Then there's another sample of 150 voters of young people between the ages of 18 and 25 that were asked the same question, and 63 of them answered yes. A pollster wants to know whether the proportion of voters who support an increase in Social Security benefits is greater among older voters. He will use the alpha equals 0.05 level of significance. Notice that there are 2 samples here. Notice that you're doing a hypothesis test. Also notice that we're dealing with proportions in this problem. You actually see the word proportion as opposed to the word mean. Okay, it's really nice in the problems when we're given what we're going to, established as our group 1 and established as our group 2. Sometimes we've seen that we have to do that on our own, but here it says let P1 be the population proportion of older voters expressing support, and let P2 be the population proportion of younger voters expressing support. So let's state our hypotheses given that right there. So our null hypothesis is going to be that there is no change, that there's no difference. In other words, P1 is equal to P2. And the alternate hypothesis is going to be found if we look back in the problem. It says the pollster wants to know whether the proportion of voters who support an increase in Social Security benefits is greater among the older voters. So since the older voters was group 1, we can say comfortably here that P1 is going to be greater than P2, but that's only because the older voters were group 1. So those are the hypotheses, and we are going to say stat tests, go down to 2PROPZTEST in number 6. Group 1 is our older voter group, and so since that has been established here in the problem, we know that we are going to put in the 95 first and then 200. Remember, x is always the smaller number because x is the number out of the total in the sample that satisfied a certain characteristic. And then in group 2 we had 63 out of 150. You want an alternate hypothesis that is greater than P2. So we can just go press calculate here. And we get a p-value of 0.1531. So it's a relatively low p-value, but it's not low enough because we'll notice that that is that is a p-value that is greater than, I better fix that, 0.1531 is greater than 0.05. If 0.1531 is greater than the alpha cutoff, then that p-value was not low enough for us to reject the null. So we would say we fail to reject the null here. That is our interpretation of the p-value because the p-value is greater than alpha. And our conclusion would be it is inconclusive. It is inconclusive whether the proportion of voters who support an increase in Social Security benefits is greater among older voters. So I'm just going to say it is inconclusive, but again, that stands for it is inconclusive whether or not the proportion of people that support this increase is going to be greater for the older group of people.